Math 1332, Chapter 3, Symbolic Logic. Section 3, Types of Statements. Video 2, Logically Equivalent Statements. Now, some of you might recognize that I used this phrase in a previous video, so it's about time that we give it its due justice. In a previous video, I liberally used the phrase logically equivalent when referring to some pairs of statements without actually defining that phrase. Specifically, I had said that the biconditional P if and only if Q was logically equivalent to the conjunction if P then Q and if Q then P, which also explains why it's called a biconditional. It's literally two conditionals. At the end of the video, we had the following truth tables for these two statements. Let me unhighlight everything except the two statements. But we had the truth tables for them. One of them, the truth table for the conjunction, took a while to build. And you may recall that this was the first truth table that we actually built from scratch that was beyond just a basic truth table. And then we said, well, since these are logically equivalent, then this is the truth table for biconditional. At which point we came up with the rule for biconditional, which said it's true if both halves of it have the same truth values. When I did that, I was actually defining logically equivalent without telling you. Two statements are said to be logically equivalent if their truth values match whenever the truth values of their simple statements match. Allow me to explain. Excuse me. If the truth values of the simple statements match, they're both true in these two rows, then the actual statement's truth values match. For example, if we go to the third row, if the simple statements have the same truth values in each of the compound statements, in this case P is false and Q is true, then the compound statement itself has the same truth value. That's a mouthful. Two statements are said to be logically equivalent if their truth values match whenever the truth values of their simple statements match. But there's an easier way to say that. In other words, two statements are logically equivalent if their truth tables have matching final columns. And that's what you should really latch on to. Logically equivalent statements have matching final columns. Because to answer the question, are these statements logically equivalent, you'll be asked to build a truth table for each and compare their final columns. So let's do that. Are the following statements equivalent? Statement 1, it is not the case that I am Texan and I am 40. There's a phrase we haven't seen lately. I'll remind you how to interpret that in a moment, symbolically. The second statement is, I am not Texas, I am not Texas. You're correct, I am not Texas. Let me go in and fix that. That's better. No, it's not. That's better. Statement 2, I am not Texan or I am not 40. Well, let's just think of it this way. Let's say that I say this statement, I am Texan and I am 40. But you know that's not the case. In other words, you know I'm telling a lie if I say I am Texan and I am 40. What would have to happen to make me wrong there? Well, if it were true, being an and, both halves would have to be true. So for me to be lying, I would only need half of it to be wrong. In other words, either I'm not Texan or I'm not 40. But enough hem-hawing about the words. We have symbolic logic, so we don't have to get trapped up in words. We remove the words, which remove biases and influences, and then we attack it symbolically. So let's do this. If we're going to determine if these are equivalent, we need to build a truth table for each one and see if the final columns match. But in order to do that, we need to define or at least locate the simple statements that these two compound statements are alluding to. It looks like the simple statements are I am Texan and I am 40. So let's let P be the statement I am Texan, whatever you interpret that to mean. To me, it means born in Texas, but maybe you got here as quickly as you could. And Q is I am 40. So how would we represent each of these statements? Well, the second one's easy. It's an or, and on both sides are the negations of those. So the second statement is negation P or negation Q. So that one's the easy one. The first one, it depends upon whether or not you remember how to interpret the phrase, stop that. It is not the case that. You may recall, let me clean this up. Much better. You may recall that the phrase, it is not the case that, not only translates to a negation, but a negation in front of an entire compound statement. And if you notice, there is a compound statement after that. I am Texan and I am 40. So how would we translate that? Well, that's easy. I am Texan is P, and is a conjunction. I am 40 is Q. So the sentence, it is not the case that I am Texan and I am 40, or rather the statement, would translate to negation of the conjunction of P and Q. Now for each of these, we would have to determine the correct order in which to set up the columns of the truth table. Clearly, I've already got them set up, but let's just talk through the hierarchy of connectives real quick. In the left table, we have parentheses, so clearly we would go inside there and do that first. And then outside is the negation, which we do second. So it shouldn't surprise you that underneath here I have the conjunction. And in the other table, we've got two negations and a disjunction. There are no parentheses. So we go to the negations first from left to right. First, second. And then the disjunction will happen last. So it shouldn't surprise you that this first column is the negation of P and the second one is the negation of Q. All right, now let's fill out both of these truth tables efficiently. The first column in the first table is a conjunction. The rule for conjunction is it's true if all T's. We are looking at columns P and Q. So we are looking at these two columns and looking for anything. And I don't know where the T went on the bottom, so let's fix that. T if all T's. We're looking at the first two columns and we're looking for any row that's all T's. That would be this first row. It's the only row that's all T's, which means it's the only row in this column that is true. The more you build truth tables, the faster you can build these columns. I am not kidding. All right, for the last column, it's just a negation, but it's the negation of this parentheses, which means it's actually the negation of this column over here, which is pretty straightforward. Just change all the truth values. False, true, true, true. So there's our first table's last column. The other table is going to be pretty easy, especially the first two. This is just the negation of P. So if we negate the P column, we get FFTT. This is the negation of Q. So if we negate the Q column, we get FTFT. And then the last column is a disjunction, and the rule for disjunction is it's false if all F's. We are just looking in those most recent columns, so let's cover up this so that we don't accidentally look at it. And now let's play out our rule. Are there any rows that are all F's? Because that's what our rule is looking for. Only the first row is all F's. So only the first row follows the rule and ends up being false. Everything else ends up being true. And now focus on the final columns. Do they match in truth values? Yes, they do. Both tables had a final column of FFTT. So what does that mean? That means that these two statements are logically equivalent. Since the truth tables for the negation of the conjunction of P and Q and the disjunction of the negations of P and Q have the same final columns, this means the statements are logically equivalent. Now, obviously, two statements don't have to be logically equivalent, but if you are asked, are these statements logically equivalent, you're looking to see if the truth tables have the same final columns.